Right, so this is problem 9 of IChO 51, and so we have the total synthesis of this compound. Okay, let's look at the questions. Assign the absolute configuration of the stereogenic center, which is here, in this compound, and also rank its priority of the groups. So of course, the hydride, or the proton here, take the 4th priority because it has the least atomic number, followed by, the amine here is going to take the first because it has the highest atomic number, and this has both, they're both carbons, so we need to consider the groups that are coming out of this carbon. So the first here is a CHH, and for the second here is a OOO, because don't forget, a double bond means 2 bonds to the same atom. So this will take the 2nd priority, this will take the 3rd priority. And let me rank here. So that's going to take the 1st, 2nd, 3rd. Clockwise arrow, that's R. But here, the hydride with the proton is in front, so that should be an S. We need to flip the stereo descriptor. The prefix al in al-lysine refers to a relative configuration. Choose all correct statements. All natural al amino acids are levotatory. That's wrong. Al descriptor in biological compounds, they do not mean the specific rotation of polarized light. It means that when you draw a Fisher projection, in this case amino acid, the amino group will be to the left. All natural L amino acids can be levorotatory or dextrorotatory. That is correct. All natural L amino acids are S. No, all natural L amino acids are R. Nope. They are not correct. L doesn't mean that. That's not its their definition. Okay, often we only want one of the amino groups in L-lysine to react. A copper-2 salt with excess aqueous hydroxide can selectively mask the reactivity of one of the amino groups after the complex is formed. Only non-complex NH2 group is available to react. Considering that L-lysine acts as a bidentate ligand and that 2 of the L-lysines coordinate into the 1 copper-2 ion in the presence of the aqueous hydroxide, draw the structure of the intermediate complex. So copper-2 has so normal copper for S1 3d9, right? Take 2 electrons out, that's going to be 3d8. Bidentate ligand, 2 lysines. That's 4 coordination numbers, right? That's a coordination number of 4. 2 times 2 is 4. D8, 4 coordination number. That means it's a square planar complex. D8 loves square planar. D8 absolutely loves its square planar. So we can safely say that this complex should be a square planar. So I have copper right here. The metal center of a copper connected to the 4 coordinating atoms. In this case, it says it's a bidentate. So let's choose our atoms, which could be the chelating atom. The coordinating atom. So of course our first atom that will coordinate is this oxygen from the carboxylate, and it's either this amine or this amine. Personally, I think it is this amine because this nitrogen is closer to the oxygen, to the coordinating oxygen, and so it can chelate beautifully without any problems. So the copper is here, the nitrogen is here, chelation. It's not too far, but for this amine to chelate, it's quite far. It's many atoms length, so I think it's just going to be this atom instead. So oxygen from the carboxylates, and the nitrogen. Oh, don't forget the stereochemistry of that nitrogen. There you go. And 4 atoms, right? 1, 2, 3, 4. 1, 2, 3, 4. 4. The amino group. 1, 1, 2, 3, 4. I think 1, 2, 3, 4. Okay, I need to save some space. And then this complex will be a neutral complex because this carboxylate group has a -1 charge, so does this one. So this carbon 2 complex, this carbon 2 metal center should be neutralized because, well, now we have, it's still copper 2, but the complex, the whole thing, has no charge. Oh, and don't forget the hydrogen here. Fortunately, in the synthesis of that's shown below, the same amino group reacts even without the copper 2 salt, so it's trying to say that this amino group can react even without the metal center. And so we have lysine hydrochloride treated with lithium hydroxide. That's just going to deprotonate that's just going to activate our amino groups. And then we followed it with benzaldehyde to get A. So that, of course, will be imine formation. So what's going to happen here is that the how many carbons are there? 6, right? Yeah, 6. So what's going to happen right here is that I'm just going to draw COOH 1, 2, 3. Oh, wait. Draw like this. It's 1, 2, 3, 4, 5, 6. Nitrogen. Imine formation with the benzaldehyde. So that's just going to be here, and here's your imine with the benzaldehyde. Great. And next question, transformation of lysine into this compound A is a regioselective reaction because we have 2 sites that we can react. We can have it react here at this amine, or we can have it react here at this amine. And we chose this amine selectively, so it's going to be a regioselective reaction. Okay, then from A to B is that we treat it with sodium hydroxide with CBZ chloride, so that's just going to protect our amine, this amine, NHCBZ, and then we treat it with diluted hydrochloric acid. That's just going to take that group away. Hydrolysis of the imine, aqueous buffers probably will work up to get B. And this should be our B. Then treatment with sodium nitrite with acetic acid with sodium acetate will yield C. So what's going to happen here is that the sodium nitrite and the acetic acid will give you nitric acid, which just going to turn the less hindered nitrogen. In this case is this one, because this one's already protected. So we're just going to leave it alone. We're just going to turn this nitrogen into a diazonium ion, which is a very good leaving group. It's the world's best leaving group. And that the sodium acetate will come and attack in an SN2 fashion to replace that diazonium ion to form nitrogen gas and this compound. So it's just going to turn it into a good leaving group and SN2 it. Okay, from C we treat with this base, not really a base, but this amine with DCC, so that's a coupling reagent, so that's just going to couple with our carboxylic acid group. So, need to take that CBZ group right over here. Amide instead now. And then we have the benzene that sticks out from the nitrogen. Okay, that's D. What's next? Reaction with a base, potassium carbonate with water, tosyl chloride, and a base. So that first step is just going to take this acetyl group out, turn it into a hydroxide. An alcohol with hydroxyl group, and then tosyl chloride, a base. That's just going to turn it into a OTS. Okay, great. H2PD on C. That's just going to turn into an intermediate F. So that's going to take out that CBZ group. Oh, sorry, I forgot to draw a proton here. All right, is everything good? Is everything good? Yes, everything is good. So that's just going to take out the CBZ group. Good. That's F. Okay, what is the what is the role? That was from my past attempt when I was trying to do this question when I was prepping for my Olympiad camp. What was the role of DCC in the transformation of C to D? DCC is a common coupling reagent or activating agent for the amide. Tosyl chloride is used in the synthesis to enable nucleophilic substitution of a hydroxy group, meaning to say SN2 kicked out the OH group. Oh, I didn't delete that page. That was from my last attempt also. Let me delete that. Okay. Mark all possible reagents which can be used as H. Let me see what H is. Okay, so H is just a nucleophilic attack of this amine, kick out the tosyl group, OTS group. So what can we use? So we can use a base to promote the attack, right? So we can use that, the potassium carbonate as a base, or we can use sodium hydroxide also. So they both work. The base will just, when the amine attacks this carbon, kicks out the OTS group, there will be an extra proton over here. There will be an extra proton. So a base would really help deprotonate that proton away to drive the reaction forward. Draw the structure of Levobupivacaine, whatever, including the appropriate stereochemistry, and G treated with butyl bromide with a weak base will give you Levobupivacaine. Okay, whatever. So that's just going to alkylate our amine. That's a 6-membered ring, right? Six-membered ring. Six-membered ring. How many carbons are there? Oh, that should be a nitrogen. That's an amide. Benzene right over here. Ooh, this benzene is pretty. Okay, so that's just going to alkylate this nitrogen. So we add 4 carbons, 1, 2, 3, and 4. The reason why we don't alkylate the amide, because of course the amide is less nucleophilic than the amine. So that's Levobupivacaine. Okay. Part 2, the synthesis of that requires the use of enantiomerically pure L-lysine. A common method to confirm the enantiomeric purity of amino acids is the transformation into amides using Mosher's acid. Draw structures of the amide from when the alpha amino group of L-lysine is derivatized with Mosher's acid. Clearly show the stereochemistry of each chiral center. So what's going to happen here is that the L-lysine, let me copy that structure. Actually, let me copy the Mosher's acid so that I don't have to change any of the geometry of the of the bonds. So here's our Mosher's acid. So we have a phenyl group here, and then we have an OMe group in front, And at the back we have trifluoromethyl group, and this nitrogen will be the nitrogen from the alpha amino group, right? Because it says right here an alpha amino group of lysine is derivatized with the Mosher's acid. Let me see what this structure look like. Okay, I'm not going to check the stereochemistry, I'm just going to draw a dash. If it's wrong, you can correct me in the comments. COOH 1 2 3 4 5 1 2. Okay, so that's how it looks like when you have the L-lysine with the Mosher's acid. Actually, let me just check the stereochemistry. R, proton in front, that's S. Yeah, that matches. Okay, so that's the structure of what they're asking. How many products will be formed when racemic lysine and S-Mosher's acid? Consider that only the amino group, the alpha amino group, is derivatized. So let's say we have a racemic lysine. So this can either be a wedge or a dash. So you will get pure S-Mosher, so that you will get 2 diastereomers. Yeah, so you will get the diastereomer of the of L-lysine. So you will get one with L-lysine with S-Mosher's acid, and you'll get a D-lysine, which is an enantiomer of L-lysine with S-Mosher's. We don't have any R-Mosher's, it's pure, and the acid, sorry, the amino acid is racemic, so L and D, so 2 diastereomers. Choose the methods that can be used to quantitatively determine the enantiomeric purity of lysine after its derivatization. So we are testing diastereomers, which are different in properties. So you can use NMR, you can use liquid chromatography, and that's it. UV vis won't work, NMR and liquid chromatography. And you can also use TLC, but it's not listed here. And that will be it for today's problem solving video. Don't forget to like and subscribe. Thank you for watching.